Thanks everyone for coming. I'm going to talk about some work that I've been working on during quarantine. It's still work in progress, so I'd love feedback. I've been thinking a lot about what it means to model a stellar light curve with a Gaussian process, and how to do it properly. And I don't know that I have answers, but I've made some progress, and I think it's promising. So you've heard me talk a lot in this meeting and in other meetings about spherical harmonics and mapping stars and stuff. And so this is yet another one of those talks. I won't disappoint. But all my talks basically begin with something that looks like this. You have a light curve of a star that you observe with Kepler or TESS at some photometric precision, and you want to figure out what the star looks like. That's pretty much impossible to do. There are just too many degeneracies in this problem. And in fact, if I were to be given this data set and do any kind of inference, whether I'm a Bayesian or a frequentist or whatever prior I use, I'm going to get a million different results. The degeneracies there are formal degeneracies here. That means that you truly have an infinite number of maps that correspond to any given light curve. And so the one at the top left here is the true map, but in terms of likelihood, it's indistinguishable from any of these other maps. And so that's the problem with inverting light curves or trying to figure out what a star looks like from its just its photometric information. A few months ago, this paper by Gabor Basri summarized this pretty well and in pretty harsh language, saying that people should just stop trying to model stars as like one or two spots and to try to associate dips with discrete spots on the surface, because it's just impossible. I thought it was really well worded. It was a very comprehensive study of what you can and cannot learn from an individual light curve. And so if you were to take that at face value, you could probably sign off from my presentation now, because it's clearly an impossible thing to do. But fortunately, since I'm a Bayesian, I think a lot about Bayes' theorem, in the sense that my posterior and the constraints I can put on the quantities that I care about depends on two things, right? It depends on our likelihood, which is probability of a data given our model, and on our priors. And the point of the Basri paper was that the likelihood is just not informative in this case. The data is just not sufficiently constraining these parameters. And so I would say that what we need to work on is our prior then. And one way to do this that I've been thinking a lot about is that all these degeneracies that are present in this problem are very strongly dependent on the stellar inclination. So stars at different inclinations have completely different light curves, but also the things that you can and cannot learn from those light curves are different depending on the inclination. And so here's the plot with the spherical harmonics that all my talks have. What this is showing is, so the spherical harmonics are arranged in this pyramid. If you're not familiar with them, the degree of the spherical harmonic, which is essentially the degree of the expansion, corresponds to the rows, and then the order is the columns. Each one of these cells shows how much you can constrain that particular spherical harmonic coefficient at a given inclination. So starting at an inclination up here of, Stephanie, can you see my mouse when I move it? Okay. So starting an inclination of 20 degrees, going 30, 40, 50, all the way to 90, the opacity of each of these coefficients is how well you can constrain that in the limit of infinite signal to noise. The fact that a lot of these are pretty translucent means there are very strong degeneracies that don't let you actually know the true value of that coefficient. And the fact that these rows here are completely transparent means they're in the null space no matter what. Those are the odd modes of the spherical harmonics that cannot be probed. But the thing that I want you to get away from this is that all of these plots look different, and they depend on the inclination. So different inclinations, you can learn different things. You can constrain slightly different spherical harmonic modes. The beauty, though, is if you were to magically be able to observe the same star at different inclinations, if I were to actually sum the constraints I get from each one of these, I get this. In this case, I can constrain all of the modes that are not odd. And so this number R here, I didn't mention this. This is the fraction of the modes that you can constrain at infinite signal to noise. For any individual star at any individual inclination, it's about 10%. And it gets worse if you're thinking about smaller and smaller features on the surface. This is limited to some resolution on the surface. But the point here is that if I were able to observe a star at a variety of inclinations, I could constrain exactly half of all the information, which is a lot. I mean, like that would go a long way to helping us understand stellar surfaces.
Rodrigo, yeah. You keep saying the phrase "at infinite signal to noise." Isn't this true at any signal to noise, or what work is that phrase doing?
That phrase is saying that these degeneracies and like these limitations are inherent to the problem, not to any kind of observation. So at finite signal to noise, things are even worse. So that phrase is doing the work of, in the best possible scenario, this is as well as you can do.
Good, thanks.
Yeah. And so unfortunately, we can't move the Earth around through the galaxy so that we get a different vantage point in all these different stars. But we have lots of stars out there, right? So just with Kepler, and TESS, we've observed hundreds of thousands of stars. And there are bound to be stars that are similar in some sense. So maybe it's reasonable to assume that, all M dwarfs, all like M9s, with a certain rotation period, a certain age, certain metallicity, would have similar spot properties. If that's true, or if it's true even to any degree, we can think about doing this as a hierarchical model, as actually modeling an ensemble of light curves, subject to the constraint that their spots and their properties are drawn from the same distribution. Then what we can do is we can constrain the parameters of that hyperdistribution, accepting the fact that we'll never really know what any individual star looks like. And so the idea there is, like, this is a silly, simple graphical model that I just drew. What we're interested in are these parameters at the top. Like properties of star spots and stellar surfaces on average, right? Something about how is the size of star spots distributed, how is their latitude distributed, how is their contrast distributed. These are the hyperparameters of our model. Deeper down, right, we want to model individual spots, but these should be draws from this hyperdistribution. And so what our data is going to be doing is going to be constraining these hyperparameters by modeling all the individual light curves subject to the same hyperdistribution. And so ideally, we should be able to do this. The problem is that what we would like to compute is the probability of the data given our model, where our model is some function of parameters we care about. Like I said, the size and the latitude and the contrast of spots. This is what we want. Unfortunately, what we have is the probability of our data given the things we care about and a bunch of stuff we don't care about. And the stuff we don't care about includes like the nitty-gritty details of where every spot is on every one of your 1,000 stars, how big it is, where it is in longitude, what its contrast is, what its shape is. And so, this is intrinsic to any kind of probabilistic inference we do in astronomy. We want to be able to marginalize over all that stuff. So we want to, talking as a Bayesian, how we want to marginalize over our nuisance parameters by taking this integral. So it's the integral of, the likelihood that we can compute over all possible configurations of star spots on the surface, consistent with that distribution that we're trying to characterize. This is an extremely hard integral. And the way you would typically do this is just by sampling, right? Have a parameter for every one of your nuisance parameters, for every one of the spots on every one of your stellar surfaces, and then run MCMC to infinity, and then marginalize them out in your corner plot or something. That's very computationally intensive. And so what I've been doing is stating without proof that what we can do instead is assume that this very difficult intractable integral, which is essentially a distribution of your data, is approximately Gaussian. It's definitely not Gaussian. If you plot it, you can see that this distribution is really wonky. But hopefully I'll convince you that this is actually a reasonable approximation to make. In the limit that you have high numbers of dimensions, which we do, I'm kind of invoking something about the central limit theorem. And so the the game here now is to figure out what mu and sigma are, what do the mean and the covariance of this Gaussian are. And that is the mean and the covariance of a Gaussian process that describes stellar light curves or describes stellar surfaces. I don't have a ton of time to describe how to compute this, but I'm gonna just skip through these slides pretty quickly. You can imagine if you were to model a single star, you can imagine putting down a spot. Think about spherical harmonics, so that has a certain spherical harmonic expansion. These are the ALMs as a function of the spot radius. If I wanted at a particular latitude, I can rotate that spot up to that latitude. I can then rotate it around to put it at the correct longitude. And then I can incline the star to the desired inclination. And then there's a linear transformation that will give me the flux. This, by the way, is what I've been working on for the past couple of years, is the starry code for computing efficient stellar light curves. That's not what we want to do here, because each of these parameters is a nuisance parameter. I don't care where this particular spot is. What I want to be able to do is treat this as a probabilistic process where phi, which is the latitude, and lambda, which is the longitude, are random variables, not actually numerical variables. And so it turns out that if I pick actually pretty flexible distributions for some of these, I can solve this problem analytically. And so the idea is, whereas there's this distribution that I can't really write down, that I can't really constrain, but I can compute the moments of this distribution. And if I'm going to approximate it as a Gaussian, I just need to be able to compute the mean and the covariance. And so the mean is essentially this integral. There's some math in this next slide. I'm just going to skip right past it, and maybe we can talk about it afterwards. But it's essentially this integral over Wigner rotation matrices for spherical harmonics. There's a similar integral that you need to take that's slightly nastier for the covariance matrix. But the end result is that you're actually able to write down the mean and the covariance analytically as a function of things you care about, the spot properties. And so I think this will probably work. So this is a web application that Dylan Simon helped me set up to host on Flatiron. I can send the link around later. But basically I can change the parameters of this Gaussian process. So like this is like the mean latitude of spots. And you can see how it changes features on the surface. I can change the variance of this distribution. I can also change the spot size. And so this is all computed on the fly, which means that it's extremely efficient way. Like computing this Gaussian process is extremely efficient because things are analytic. And so you can see how that changes the maps and the light curves down here. And again, I think I only have a few minutes left, so I won't spend too much more time talking about this. Other than to say that it's still a Gaussian approximation. And so like things are a little fuzzy, they're not discrete spots, they're bright spots. But what we really care about is how well this does at constraining parameters, at doing actual inference. And so for that, what we can do is we can imagine a synthetic ensemble of light curves with spots at a given latitude and of a certain size. And then I can pretend to observe them. And so just actually do a data injection and recovery result. And so given these 50 light curves observed at finite signal to noise, there's a true distribution here that I want to constrain about the spot properties. If I run this through the Gaussian process and use that as my likelihood, remember that's the approximation that we're making, that's the Gaussian process. This is what I get. And so this is just the corner for one particular realization of the data. You can see that the spot radius, the mean spot latitude, the spot variance, spot latitude variance, the spot contrast, and the number of spots, I can recover all of them pretty much without bias. And so it's actually pretty cool that this Gaussian approximation to that intractable integral is unbiased. And it actually does a pretty good job at capturing the variance. There are some issues, but I can talk more about those later. But at the end of this run, one of the things that comes out is like, this is what I believe to be the distribution of star spots as a function of latitude on all those stars. And it happens to be very close to the truth. I timed that perfectly.
Good job. And hopefully it doesn't happen to be very close to the distribution, right? I think all those integrals told us that it should be very close, right?
So it's the distribution is definitely not a Gaussian. It's the equivalent of doing this. So I have a backup slide. Oh, that's my beeper, sorry. So it's the equivalent of doing this, right? So like this blue histogram is a beta distributed variable, which has a very asymmetric, highly peaked, finite support distribution. I'm approximating that as a Gaussian, as the orange thing, right? I'm saying that, you know, even though my data looks like that, I'm going to say that it's distributed according to the orange one and do inference with that. And there's no obvious reason that it should work because those distributions look very different, but they have the same mean and the same covariance. And if you try to constrain the parameters of that beta distribution using the Gaussian approximation, you do pretty well. And so that's this top plot here. Is the orange is your approximate posteriors and blue are the exact posteriors. It's completely unbiased, but you do underestimate the variance a little bit. And so even when your distribution is not even close to Gaussian, it works. So I'm still trying to understand why, but it's some kind of magic of Gaussians.
Very cool. Thanks. Okay, I'll clap. Yay! Thank you very much. Good job. Okay, we have time for a couple questions. Shirley, you're ready. Okay.
Can I ask, have people looked at possibly using normalizing flows for this?
That's a good question. I'm not sure. I know that there's been quite a bit of like approximate, like Bayesian computation or other approximate methods for doing this. I don't know about normalizing flows specifically, but there has been a lot of efforts to do similar things to what I'm doing.
Okay. Ooh, I don't know that we're going to get through everybody, but I'll try people. Megan, you were next.
Yeah, Rodrigo, awesome talk. And as always, I love your slide designs. I was wondering whether you could use this method to put constraints on the possible inclinations of individual stars once you have a better understanding of sort of what their ensemble should look like, because that could be really useful for exoplanet discovery.
Yeah, definitely. One of the other things that surprised me is that it actually does a pretty good job at predicting the inclinations. I don't have a plot here, but there is an issue with the variance. I think I end up predicting the inclinations with like unreasonably good precision, right? Like more precision than I should have given the true dispersion. But it's unbiased. And so yes, you can use this to figure out the cell inclination.
Great. Viviana.
Hi, well, I guess I'll say it again. Awesome talk. Very nice design. I was just curious if you guys checked how the, like the full expensive MCMC methods compares with your Gaussian processes on data as opposed to simulations.
Yeah, that's the next step is doing this on data for sure. And I could run the exact problem and see what I get. But the fact that, one of the things that I did is like you can run the same approximate inference problem on 100 different realizations of your data and show that it's both unbiased and the variance is kind of correct. And so like, you know that this is very close to what you would get solving the correct problem because you know the truth here. But doing it on real data is the next step for sure.
Great. Okay, we'll do it. Richard, what's your question?
If we're trying to generalize this to other problems like inferring parameters from very degenerate images of black holes to all sorts of applications in astronomy, what's a rule of thumb for how many parameters the space, or what the dimension of the parameter space would have to be in order to have this method give 10% of the true values? Or
Yeah, that's a good question. I think it's very problem specific. And also, the only reason this method works is because I can, because spherical harmonics are so well behaved, right? So like I can compute all those like ridiculous integrals analytically. In general, people have used this, it has different names. Some people call it synthetic likelihood. In general, what people do is they sample from their prior, or sample from the true distribution like 1,000,000 times, and then compute the empirical mean and variance that way, and then use that as your likelihood. And you can do that for any problem. The cool thing is that will work for any problem, but then the issue is that you have a noisy likelihood. And so then it's a balance between the number of parameters and the number of times you're willing to sample from the distribution to approximate the likelihood. And so if you look at the ecology literature, does this a lot for modeling population growth and population dynamics. So that might be a place to start. I know that cosmologists also do something very similar to this. I don't have a good answer, sorry.
All right, thanks, nice talk.